All right, so we're going to look at absolute and relative dating. You can also just read through this if you do not want to listen to me talk through it. Basically, we talked about the fact that as we're looking at Mount Everest way up here, you're actually going to find evidence of sea life. And they couldn't figure out how that happened. Well, we know today that had to happen because at one time that layer of rock had to be at the bottom of an ocean to get sea um, fossilized shells up there. And we know that that happens as the continents collide and through uplift. Ancient peoples had other ideas of how that got there. There was a flood, many things like that. But we know that at one point, this layer of rock where you're going to find ammonite seashells, you can actually find fossils like this at the top of Everest, were at one point underwater, and through uplift, through continents colliding with one another, they were raised up to the height of Everest. So we understand those processes of seafloor spreading and subduction, and the creation of the Himalayas as the Indian Australian plates literally collides and so is subducted under the Eurasian plates. But remember, mafic material is less dense, so it's forcing it up because both want to float on top. And so literally it just has one plate being pushed underneath another, and then it breaks. And then another piece starts to get subducted, and then it breaks and it forms these ridges as the mountains rise up. This should be familiar from last unit. So then I'm going to ask you a question. By the way, this means match all that apply. Earth's immense age allows for that slow processes of continental drift, and why we can see that evidence of fossils at the top of Everest. And we can also look in the Antarctic, and we find fossil evidence there. Now, the Antarctic is technically a desert. It gets less than the required amount of precipitation to be more than a desert, but because it's so far at the bottom of the world and it spends, almost 6 months of its year in darkness, it doesn't melt more than it gains. So, but technically it is a desert. So below we see a day in the Antarctic. There's no animals, there's no plants living here. It's still too cold and it's too arid. But yet we find fossils. So we also know that it was a much, much warmer time because we actually had a polar allosaurus there. And as you know, reptiles depend on the sun for their energy to heat them up. They don't have an internal temperature like we do that keeps us warm. That's why we're warm blooded animals, and dinosaurs and reptiles are cold blooded. They just can't regulate their own temperature. So you should not find allosaurs at the South Pole unless at one time that climate was much warmer than it is now. So that's a piece of evidence that tells us the continents moved. And then remember, we've got the whole fit thing where, here South America, and remember this before, like the Mesosaur you can find between South Africa and South America, and the Glossopteris fern goes all the way through here. This is a review. I'm not going to spend a lot of time on it. And then this, if you watch the intro video, would this be, you should be asking yourself, is this tension or compression? In other words, is this a um, pull apart, a rift area, or is this a subduction zone? And you should know by the movement of this, with this magma plume coming up, we get convection currents rolling off this way and rolling off this way, pulling the crusts apart. So this would be under tension, and this would be a rifting zone. So those whole mechanisms that we've been talking about all come together to, form the things that show us what happens on Earth. It's all interconnected. So law of superposition helps us understand the age of the Earth, its layers, and fossils. And as long as there hasn't been uplifting or tilting, and sometimes they can literally be flipped upside down. But for the most part, the general rule is oldest layers at the bottom, newest layers are at the top. So the deeper we go, the older the fossils also tend to become less complex. The higher up we get towards modern humans, the fossils become more complex. So if you're looking down here, we have a hard time in the Paleozoic, before the Paleozoic, in the Precambrian actually, finding a lot of very well-preserved fossils, because we're talking a lot of single-cell organisms here. They just don't preserve that well. It's not the right kind of body. It's better if you have hard parts to be preserved. But as we go up into the Cambrian and the order, so here's this quick preview of what's coming up. Precambrian is really down here. Then you've got the Paleozoic. There was a mass extinction event about 2.5 million years ago, basically. And we had 95% of all life. We believe there was a meteor impact, and then which triggered some massive volcanic eruptions, spewing more gas and ash, which cooled our temperatures down and smothered some sunlight. But the reason why we actually change an era is because there's a mass extinction event happening. We lost 95% of all life here. Only 5% from the Permian made it into the Mesozoic, into the Triassic. And this Mesozoic, these three periods here, this is the age of the dinosaurs. Now, at the end of Mesozoic and into the Cenozoic, which is our timeline, our era, we had another mass extinction event, not quite as bad as the Permian, which is 95%, but this is where we lost the dinosaurs as we know them. Now, remember, birds are actually descendants of dinosaurs. So if you take, I think it's something like, if you're really, really hungry at Thanksgiving and you make 3 turkeys, if you take 3 turkey carcass, the skeletons, you can actually create your own dinosaur. You'll have enough bones. You just won't have the head. So, Precambrian down here, not a lot of life seen and preserved because it's just really long ago and it was very simple. Get into the Paleozoic, we actually start to see more complex life starting to come into existence. These things are called trilobites. And in that, we've got the Cambrian, the Ordovician, the Silurian, the Devonian, the Mississippian, the Pennsylvanian, and the Permian. Those are the periods of the Paleozoic era. Dinosaurs are split into 3, where you actually see distinctive types of dinosaurs at this point. You have the Triassic, the early, the Jurassic, the middle, and the Cretaceous, the ones that were at the end. And this is the 3 periods that make up the era of the Mesozoic. Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, and Heliocene. Now, we actually can split these into 2 bigger ones, but this is how archaeologists would split this up by different fossils. So down here, you're going to see saber-toothed cats, but up here, you're not going to. So superposition says the farther down you go, the older you get. The farther down you go, the less complex life is. The higher up you go, the more complex life. The higher up you go, the more recent it is. So that's the law of superposition. So not all fossils, note, so that all fossils older than 300 million years are basically marine and water organisms. So once you go past that mark, we don't really have a lot of animal life that you would consider on land at that point. You could find plant life that actually colonized the upper air layers earlier. This is law of superposition. So basically, okay, down here should be the oldest, right? So shale 1 should be the oldest. The next oldest should be sandstone 2. Now you would think that shale would be next, but actually this is an intrusion. It's technically called a granite dike. And it's basically, we had hot magma come up and melt its way through, and it melted through these 2 layers, but you'll notice that this is a nice cross cut. The erosion happened up here. So this is the 3rd oldest, and this 3rd layer of shale capped it, okay? And then the lava flow came, and then the limestone came as the youngest layer. So oldest down here, youngest down here. So I'm going to ask you some questions. Can you figure out what's what? What's older? Well, this intrusion has to be younger than sandstone 2 and shale 1, but it's older than shale 3. Okay, so that's important. That will be a test question. I can guarantee you'll see that on the test. And so if you look here, you can tell, relatively speaking, we have something called index fossils. And if you find the same fossil across continents, you have a rough idea of the age of that fossil. So if I can find this trilobite here and then I find it somewhere else, but you'll notice that layer's missing over here. But see the ammonite and the fish, and I can't quite tell what that is. It's a shell of some kind because it says up there in the key. That's the bottom layer over here. So somehow this bottom layer here that's on the left side is not on the right side. So we know that this layer lines up with this one. This is probably a lava flow. It's actually extrusive lava flow, if we look at the key up here, happened across both of this. This layer is also missing over here, and this volcanic layer is missing. But then as we go to the two new layers, they are on this side. So this side has had more erosion, but it also means that if this set of fossils and this set of fossils all line up along with these, at some point these were connected. But we're missing some layers here as we have there. There's also, if we look at those different ages, if we go up back and look at this, there's one of these that's actually right here, the Pennsylvanian and the Mississippian. These are not in the European set because we have more strata in the US, guess where? Between the Mississippi state and the river, and Pennsylvania, where we actually see distinctive layers with additional fossils that are not found in Europe. So we know that we could actually subdivide that into two parts. And the one that I would teach you, I wouldn't actually make you know the Mississippian and the Pennsylvanian, but you need to understand that they do exist because of this reason, that sometimes some continents actually have more erosion at time and they lose layers that other places did not lose. So index fossils can be used to determine the age of the soil layers around it. So if I know the index fossil is absolutely this age, anything lower than it should be older and anything above it should be younger. So index fossils lived usually for a brief period of time, but they were widespread. And that's a really good indicator for an index fossil. Here's a trilobite. In this case, you could have gastropods, these, or you could have crinoids, which was a kind of like a cross between a plant and a coral. And then we can find more gastropods on this layer. And you'll see that this coral comes up to here, but it doesn't make it through over here. And here you're starting to see ammonite shells. So we know we're in a different era because now all of a sudden ammonites have appeared. So we know this stuff down here has to be older than ammonites. But you'll also see that some of these things have made it through multiple areas. Now, if I find this particular ammonite on the European continent, and then I find this particular same ammonite on the North America continent, we know that at one point those had to be somewhat connected, and that was actually a shallow sea. Interestingly enough, and I've told you this before, in Minnesota, you will never find a dinosaur fossil. You have to go to South Dakota for that, because at the time of the dinosaurs, Minnesota was a shallow tropical sea. We were much closer to the equator, and we were under saltwater. So you will actually find marine fossils in Minnesota. So we know that the trilobites were the oldest fossil because why? You should be asking yourself. The law of superposition tells us that the farther you are down, the older it has to be. So law of superposition says this has to be older compared to everything above it. And these ammonites have to be younger than everything it's above, but older than the stuff above it. So again, some questions to ask. Now we're going to get into law of superposition helps us determine relative dating. The farther down we go, the older it is. The higher up we go, the younger it is. So radiometric dating tells us absolute, within a range of how old something is. And by the way, you are going to have to go through these notes. Do not forget to go answer the questions or you will not get credit for this. So radiometric dating uses radioactivity trapped in materials to determine how long ago it formed or died. We eat food, whether you are a herbivore or a carnivore or an omnivore. In other words, if you just eat plants, you are consuming carbon. If you eat animal products, you are also consuming carbon. So no matter what your diet is, you are consuming carbon. And with that, we keep our carbon levels constant because we're constant. If we don't eat, we don't make it. But when things die, our carbon levels no longer get increased and we start to lose carbon and it decays, and we can radiocarbon date like mummies to find out how long ago they died within a range period. But rocks will use things like uranium trapped in their crystals as they formed, and that uranium slowly decays into lead at a predictable rate. It's called a half-life. And so in this case, Uranium-235 breaks down into lead-207, and its half-life is 704 million years. Now, there are other forms of uranium that actually have a half-life in the billions of years, so be careful of which uranium you're using. So a half-life is simply this. I start out when it cools with 100% uranium. A half-life is when half of it has changed into lead. That's its half-life. How long does it take for half of it to change? In this case, 704 million years. So it can actually have multiple half-lives, because now if I take half of what's left, my 50%, and cut that in half down to 25%, I've hit my second half-life, which would be another 704 million years. So now half of what I had left is gone, which means 75% of my product, my parent product, has been converted to the daughter product. So here's two new words. The parent product is my uranium. My daughter product is what it breaks down to, which is lead. And so at this case, I'm 50-50. After a second half-life, now I'm 75 lead and 25 uranium. I can take that half-life again. What's half of 25? Well, it's 12 and a half. So when I get to that next half-life at 12 and a half, now I am 87.5% lead and only 12.5% uranium. So that's after 3 half-lives. And, you know, fractions are fun, and you can go, you know, you can half your 12 and a half and your 6.25, and you can half that, and you keep going and going and going. You technically never really reach zero if you keep having, but at some point you do run out. But that's unpredictable as it is. So our curve breaks down really fast. But a half-life is how long something takes for half of it to decay. So the more lead there is in rock versus uranium, the older the rock is. So radiocarbon dating, we talked about this, uses carbon-14, which is what we consume. All living organisms eat carbon. And until we die, at that point, the organism stops taking in. And so carbon-14 changes into nitrogen-14. And if we go to 50%, which is right there, it's a little over, if I follow this down, so here's 50%, follow it over where the line for the decay rate for carbon-14 is, follow it straight down, and it's a little over 5,000 years for carbon-14's half-life. So after 5,000 years, I'm half carbon-14 and half nitrogen-14. At 25%, that's my second half-life, a little over 10,000 years. Now I am, again, 75% nitrogen-14, the daughter product, and only 25% carbon-14. And after another half-life, another 5,000 or so years, I'm at about 12 and a half, about here. Now remember, I'm about 87% daughter product of nitrogen-14, only 12.5% of the parent product, carbon-14. So every time we have a half-life, half of what's left changes into the other daughter product. So 50, 25, 12 and a half, 6.25, and you can keep going. So newly dead, lots of carbon-14. Long time dead, not as much carbon-14. And there is a range within that. If you watch this, and I'll have you do that in the video, this is actually, I explain it talking about decay rates of one, and you can see the bucket change. So please go ahead and watch that, or I guess I could do it here, but that's just going to take a little bit of time. Decay rates. We can actually look at the half-life. In this case, we're doing carbon-14. So you can see, what you're going to see is that chart keeps going, and it shows you the decay rate. So please make sure you play that video. This one is using actually absolute dating. With a microphone I can go through, and then relative dating tells me the stuff down here should be older than the stuff on top. So again, please watch that video. Here's questions that go with that. Here is a YouTube guy talking about decay. Here is using relative and absolute dating. So if I take the uranium in this lava flow compared to this one, I know this happened 510 million years ago. I know this happened 495 million years ago, which means this needs to be just over 495 million years, but not as old as 510 million. So I can use absolute dating in conjunction with relative dating, remembering law of superposition says the farther down we go, the older it should get, and the absolute dating is confirming that. 495, 510, 520, 400, 545 million years ago as we go down farther. So we know that these trilobites have to be between 520 and 545 million years old. Again, more questions to go with that. Watch this guy. Okay, then we're getting into ice cores and varves. Basically, as we pollute, you actually find our modern day pollution landing in the ice in Antarctica. But the cool thing is, as those layers compress, they actually form bands like a tree ring does every year. And we can actually see there's melting and then there's a crewing, and they form these bands. But the cool thing is, within that ice, it actually traps gas particles from when that ice formed. So as we take these ice cores and we, under very careful conditions, will pulverize it in a vacuum tube, it releases the gases. And we can actually see the composition going back about 400,000 years of our ice samples to find out the composition of the atmosphere. It's one of the reasons why we know we have a lot more greenhouse gases now than we did before. So if I read this, ice cores formed during glaciation periods, creating layers. So each layer has a light and a dark band. That's that freezing and thawing. Light bands are the summer where we have melting. Dark bands are the winter where we have accrual. And you can see the layers starting to build and form. And this is the start of a glacier. And it's actually, there's snow. And then as it gets kind of crystally, it turns into something called neve. And then as it goes down here, eventually it's under enough pressure, it forms glacial ice. So these bands can be up to 400,000 years old, and we can find them this thick in the Antarctic and Greenland. And that trapped air really allows us to see what's in that bubble and what ancient atmospheres are. We can analyze that material. That's important. Watch this guy. He's actually looking at some ice core samples. And we see from that, here are our correlations. Now, this is the wobble effect, if you remember back from astronomy, of when we are slightly farther and closer away. That's a natural progression. We naturally do get warmer and colder. This is true. It does happen. But you'll notice there's a pretty consistent pattern over the last 400,000 years, except now we're still technically in a cold area, but we're getting warmer. And we've never gotten this warm or have this much CO2 trapped as we do right now, or as quickly. It's never happened this quickly before. That's the difference between past paleoclimates and global change of temperature into warming and cooling versus today. It's the speed at which we're changing and the level which our planet has not seen in the past 400,000 years. So again, answer some questions and then you're done. As always, email or Zoom if you need help.